All right, so we're going to move into synthetic division, okay? Shortcut with polynomial division, but only works in very specific cases. And we use this for some theorems that we're going to cover a little bit later. Factor theorem, rational zeros theorem, things with some polynomials. So there's a lot that builds on synthetic division. Synthetic division, while it is a shortcut, is also a very important cornerstone in some other stuff that we're going to be doing, okay? And even as you go into more advanced math, synthetic division becomes more and more useful. So, in order to find the quotient and remainder of a polynomial of degree 1 or higher divided by another binomial, we can use synthetic division. So the requirement in order to do synthetic division is our divisor must be in the form of x minus c. C is just some constant, okay? What's important about this is a couple things. One is that it must be a binomial, 2 terms, and only 2 terms. The second thing is it must be of degree 1, meaning there's no exponent there. Third thing is the leading coefficient has to be a 1. We cannot have any other number in the front. Can't even have a negative. It has to be a 1. Okay? So in order for us to do synthetic division, we have to have a binomial in that form. So I could have something like x minus 3, or I can have x plus 2. Those are fine. I can do synthetic division with those types of binomials. I cannot do synthetic division with something like negative x minus 3, or x squared plus 2, or even a trinomial, x squared plus x plus 2. Those we cannot do synthetic division with because they do not meet those criteria. Leading coefficient of 1, greatest degree of 1, and it is a binomial. Has to meet all 3 of those. But as long as that's what we're dividing by, then we can use synthetic division as a shortcut. Okay? So, this is how we set up synthetic division. We take out all the variables in the exponents and we get rid of them. Okay? We're going to focus on just the coefficients and the constants. So that's the first major difference. We strip out that. Now, if it's subtraction, note that we have minus, negative signs here. And we have subtraction, so that still remains. Okay? Second thing that you'll notice, hopefully, okay? So right in here, we have our dividend. All right? Those are the coefficients and the constant of our dividend. Okay? What we're dividing. Then outside, we have our divisor. Okay? But what do you notice between the difference between this and this? The 3 is negative there, but it's positive there. Right? This is why. This is why. We switch the sign because we're not actually dividing by x minus 3. What we're doing is we're dividing by the root or the solution to our divisor. If I take x minus 3 and set it equal to 0, what does x equal? 3. If we look back at our formula from before, remember how I said it has to be in the form x minus c? That's the form it has to be in. And we compare x minus 3. Well, if I look and I say, okay, well, my c value, that's what this is my c value. Okay? Well, if negative c equals negative 3, there's a sign change. C equals 3. So that's the number that's going to go in. So when we're doing synthetic division, we need to remember the sign change here. There is a sign change here. All right? And now, since we're on the topic of sign changes, yesterday, when we did our division, what was step number 3? First we divided, then we multiplied, then we did what? We subtracted. Okay? On synthetic division, we don't subtract. We add. Okay? So we're doing some sign changes, so we need to keep that in mind. But as long as you remember that, synthetic division, if it's something that's allowed, is significantly faster. Okay? So here's the process. All right? We add, and then we multiply. And that's it. We do that over and over and over until we run out of steps. Okay? So starting with the first column, we want to add to get down to here. Well, 2 plus nothing is what? 2. So a lot of times you'll see you bring down the first number. We're just adding. We're adding 2 to nothing. We haven't done anything yet. We're bringing down the 2. Okay, we add it to nothing. So next step is to multiply. Multiplication will always happen with our C value and whatever we have down here. Okay? So everything in that bottom row is going to get multiplied by our C value, which in this case is 3, and that's going to create the next number for the row above. That's going to make the next number for the row above. So we're going to do 2 times 3. What does that give us? 6. 2 times 3 gives us 6. And now we go back to the beginning. We add. What's negative 1 plus 6? 5. And then we multiply again to get the next number. 5 times 3 gives me what? 15. And then we go back to the first step. We add. Negative 13 plus 15. And then we, next step after add, multiply. What are we going to multiply? Not 2 times 1. 2 times 3, which gives me what? 6. And then we add. And now we have another line. We're done. Okay? And here's where the magic comes in. Whenever we divided, whenever we did long division, we divided x to the third divided by x. Okay, x to the third, something, 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 right? We have x to the third, blah, 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 divided by x, blah, blah, blah. Okay? When we do that division, x to the third divided by x, what does that equal? What's x to the third divided by x? X squared, right? So our quotient was always 1 degree less than our dividend. 3 to 2. Okay? Well, I'm dividing x to the third by x, so my quotient's going to have a degree of 2. X squared. We went down by 1. So these numbers down here, 2, 5, 2, actually let me make some more space. 2, 5, 2, and 7. Those are the new coefficient, constant, and remainder of our quotient. But since we know that if I divide, my leading term is now going to be a squared, we know that this is going to be x squared. And then we just follow down the line. Well, what's lower than x squared? X. And then after x, we have the constant. Okay, well, I have the constant here. That's going to make 7 my remainder. 7 left over. And so with the division, we get our quotient as 2x squared plus 5x plus 2 plus 7 over my divisor of x minus 3, and then we've divided. So once you get the hang of it, it is a much more condensed method of division. It will become much faster, because it's just add, multiply, and then put your variables back in. Okay? Say we were going to do long division with this divided by this. Okay? So if I have x minus 3 on the outside, and then I have 2x to the third minus x squared minus 13x plus 1. What's our first step in long division? Divide. What am I going to divide? Okay? So that divided by that. What does that equal? because that's going to be a lot faster. And the point of synthetic division isn't just for a shortcut. It's because long division, well, now you're going to increase the amount of time it takes to complete whatever that task is. Synthetic division is a lot faster. It's also a lot more reliable because there's less versus this is the amount of space it takes to do a synthetic division. The same thing on long division would probably take up that whole space. And it's 4 steps on a repeat versus 2 steps on a repeat. So let's set it up. So when you're setting it up on your own, you draw the box, and then you're going to draw this line right here. Okay? First, we want to get rid of all the variables and all the exponents. Okay? And just look at the coefficients and the constants. Well, we start with the first one. What's the coefficient on x to the 4th? It's a 1. There's our coefficient. So we put a 1, we get rid of the x to the 4th. What's my next coefficient? We put a -3, get rid of the x to the 3rd. What's our next coefficient? -13, get rid of the x squared. What's the next one? Get rid of the variable, and then our constant, 32. You strip out all the variables, all the exponents, focus on your coefficients and your 1, -3, -13, 6, 32. Okay? Now, our C value is what goes in the box. -3. What was step 1? Add. Well, 1 plus nothing is what? 1. Step 2. Multiply. What am I going to multiply together? This one down here with that -3 to get the next number in the second row. All right? Now what? Add again. What do we get? -6. And then we... What do we get? Good. Then? Yep. And then? And then? And then? And then? -3 times negative. Give me one problem we did yesterday that was faster than that. The one we had with x to the 3rd power was longer than that. And this was x to the 4th power. So much faster. So all we have to do is put our variables back in. So again, look at what our leading power is. Knock it down by 1. So what's our degree going to be on our quotient? X to the 3rd. What's after that? And then the next one? The next one's our constant. What's 59? The remainder. X to the 3rd minus 6x squared plus 5x minus 9 plus 59 over our divisor, x plus 3. If we would have done that with long division, it would have taken up that entire page. Assuming we didn't make any mistakes. So, long division will always work, but it's a lot longer. If we have a divisor in this form, you can and should use synthetic division. Okay? You can and should use synthetic division. Now, if this was anything else, if this was a 2x plus 3, we couldn't use synthetic division. So we have to do it. But that wouldn't be very helpful for a lesson on synthetic division. All right? Set it up. What's going to go inside the box? Positive 4. Okay? What's my first coefficient? Good. What's my next coefficient? Good. What's my next one? Good. Why is there a 0? It fell on the spot, right? So this is 6th power, 5th power, 4th power. We're missing our 3rd power. We've got our 2nd power, but we're missing our 3rd power. So we need a placeholder 0. Then we've got our 17. Okay? So we've got our second power. But now we're still missing our first power. So we need a placeholder 0. And our constant. We need to account for every single degree in that polynomial. So when you see what the largest number is, make sure you can count from that all the way down to 0. 6, 5, 4, 2, 1, 0. Those are all the degrees. You need to make sure you have every single one of those accounted for. If you are missing even one of those, complete the wrong answer. Okay? Now I'm going to rewrite that so I have a little bit more room because I went too far to the left. Minus 25, 35, 0, 17, 0, 0. All right? Okay? All right, so step 1, add. So what are we going to start with? 4. Next is, keep going. Took us, I think, legitimately less than a minute. Our quotient. Added, and then we multiply. Then we added, then we multiplied. We added, then we multiplied, then 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 we added, and we're done. So, on my quotient, what's the leading degree going to be? 5. So, we start with power of 5. Then we go down to power of 4, and then a power of 3, and then a power of 2, and then a power of 1, and then our constant, and then our remainder over our divisor. Oh, yeah. All right, so now, this is why synthetic division is useful. It speeds up these two processes. Okay? We're going to talk about the remainder theorem and the factor theorem. Okay? Remainder theorem is another simplified shortcut for evaluating for specific values of functions, especially when we have a large degree polynomial, where we've got 6, 7, 8 terms in it. Okay? What it states that is if we take a polynomial and divide it by a binomial in the form for synthetic division, whatever our c value is, if we evaluated that function for c, the remainder is the solution. Okay? That's why we call it the remainder theorem, because we're looking specifically at the remainder. Okay? Now, if that remainder is 0, the factor theorem states that that polynomial is a factor, okay, that dividend or divisor is a factor of the dividend, which is how we divide polynomials above second power. We can factor quadratics, but we don't have any method for factoring 3rd, 4th, 5th, 6th degrees. Synthetic division is that process. Synthetic division is how we factor those things. We use some tricks and tools and things, which we'll do a little bit later. We'll go into more depth in that. But we'll use some tricks that we have to identify factors. Then we use synthetic division to factor it until we get a quadratic, and then we factor the quadratic. So using synthetic division, you essentially have the tools that you need to factor any polynomial of any degree. It would take a long time, but I could give you a polynomial of 20th degree. You could technically factor it. Those are the only tools you need. Synthetic division. So, get your calculators out. We're going to have a race. Here's what you're going to do. So, P of 3. What does this 3 mean? not going to multiply everything by 3. What does that 3 mean? X equals 3. So if I wanted to evaluate P of 3, I would take that 3 and I would plug it in for every value of X. And I would solve it. Okay? So what I want you to do on your calculator is I want you to plug in X with 3, and I want you to solve it. I want you to give me the answer and let me know if you get the answer before I get it. Dude, you cheated. You started early. Done. Keep going. Finish. Now, another thing I've noticed, because a lot of students will just plug it in my calculator. Most of the time, especially with that, if you're not really, really careful, you're not going to get 270. You're going to get okay. Especially if X was a negative number. If X was negative, the chances of you getting the wrong answer when you plug it into your calculator goes up really high. Because now you have to make sure that you're putting in parentheses in the proper spot. Make sure you get the exponents. Don't forget your subtraction signs. It's really, really easy to make a mistake. Synthetic division allows us to evaluate these much larger functions more quickly and more reliably. Okay? It's not just because I want you to do something new just for fun of it. I want you to have something new because it is another better tool in the toolbox. Evaluating with your calculator, believe it or not, is you using a manual drill when I just gave you an electric one. Okay? This requires a little more effort on your part, but it's going to be faster and it's going to be more reliable. So we set up synthetic division. I want to note a couple things. Okay? They gave us C. When they give you the value for C, there is no sign change. There's no sign change. Okay? 3 is 3. We still set up synthetic division the same way. Our coefficients, I've got 6, 5, 4, 3, 2, 1, 0. Okay? I put in my placeholder zeros. I stripped out the variables, checked my signs, make sure everything's good. We add, we multiply, 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 we add, we multiply.
When they give you that 3, like what are you supposed to put?
So for this, we're not writing the quotient. So the answer is 270. That's it. We're not writing out the entire quotient. We could if we were doing the division. And if we wanted to work backwards, think of it this way. If X equals C, they gave us C, right? So X equals 3. If I wanted the divisor, well, I just need to move this back over here. Well, how do I move 3 back to the other side? Minus. So that's your divisor, okay? That's how we get our C value. So we can work backwards from that. But when we're using the remainder theorem to evaluate, the answer is literally just the remainder. That's why it's called the remainder theorem. So P of 3 equals 270. Okay? And I want to be very clear, especially on an assignment or an assessment where I say, use the remainder theorem. If I don't see synthetic division, you're not getting credit because then you didn't use the remainder theorem. Does that make sense? Now, to expand on that, we're given this polynomial, and we're going to use the remainder theorem to show that 4 is a solution to the equation. What it means by if 4 is a solution, it means the remainder is 0. Okay? So it goes back into the remainder theorem. If the remainder is 0, then that value is a solution to the polynomial. So I've got the synthetic set up for us, and we just need to go through and show that 4 is a solution. All right? So we're going to go through, we're going to start with adding. So what am I going to end up with first? 2. Then what? Good. Then what? There you go. Then what? Then negative 20. Good. 12. And then? Okay. My remainder is 0. That means that 4 is a solution. 4 is a solution. Right? And even more importantly, if 4 is a solution, it means that x equals 4, right? X equals 4. 4 is a solution. X equals 4. Well, let's do what we just did, and let's write that back in the form x minus c. What's my factor going to be? It's 4, right? If 4 is a solution, that means that x minus 4 is a factor. X minus 4 is a factor of that polynomial. Okay? And even more importantly, that's why I love this stuff. It just builds, expands. We get new information constantly. What is this quotient going to be? 2x to what power? Minus 5 minus 3 with no remainder. So now I have this quadratic, which is also a factor, because that quadratic times that binomial equals that function. So I've factored a third power polynomial. We factored it. And we can keep factoring it because now we have a quadratic. How do we factor this quadratic? 2 times negative 3. We look for our product and our sum. So what gives me a product of negative 6 but a sum of negative 5? Negative 6 and 1. Okay, so we can do our factor by grouping. And then 2x with x minus 3 plus 1, x minus 3, 2x plus 1, x minus 3. So we took that quadratic and then we factored it, and then we can take this one from way back in the beginning and add it to our list, and now we've taken a third power polynomial and completely factored it. That's the process for higher degree polynomials. We identify what numbers are factors, use synthetic division to divide, to factor. And then once we have a quadratic, well, we know how to factor quadratics. So then we factor. And that's how we factor higher degree polynomials. And that is why we use synthetic division, because it allows us to do that quickly and without taking an entire sheet of paper and factor 1 cubic, God forbid it's a 4th degree or 5th degree. Because the process works for no matter how many degrees. We just have to do more synthetic division steps. Okay? Now, yeah, that was that. Okay? So we use the factor theorem. That's what that is. We said, okay, we've got our factor, and now we can continue factor it, so we completely factored our polynomial. That's what we have here. All right, and now I want you to notice a couple things. Did I say factor or solve? Oh, solve! I forgot we need to solve. Okay, so we've got it factored. X minus 4, 2x plus 1, and x minus 3? Right? Was that the last one? Yeah. Okay. So it's factored. Right? So now we need to solve it. Solve means find all the solutions. Well, we already know one of them. It's 4. That was that very first step. Show that 4 is a solution. Okay? So We solve our quadratics by setting all of our factors equal to 0, right? Solve all our quadratics by setting our factors equal to 0. I don't know why I put that in there. Let's get rid of that. Okay. Well, if we solve this first one, we get 4. We already know that one's a solution. We already had it. Okay? But we needed to use that in order to factor it further, get the quadratic, then factor the quadratic. Now I have these two factors. So we can factor 2x plus, or solve 2x plus 1, and we get x equals negative 1/2. We can solve x minus 3, and we get x equals 3. So we have 4 solutions. 4, negative 1/2, and 3. Those are our solutions. So we can factor it, and once we get our factors, we set each factor equal to 0 and solve. Okay, so that's our 0 factor property. Now I want to show you something where this all ties in. Zeros, solutions, roots are synonymous with intercepts. Oh, that one's not going to work. Ah, there it is. Where are the x-intercepts at this graph? What's this one right here? What's this one right here? What's this one right here? We're finding the x-intercepts of our graph. This is essential in identifying and graphing polynomial functions, is using the factor theorem and the remainder theorem. So when you're given something like this and asked to solve the polynomial equation, then what you have to do is you have to identify what are your solutions, and then you're going to use division to prove it. So this is where your graphing calculator comes in handy and why it's necessary. Okay? It's not optional at this point. It's necessary. Because what you're going to do is you're going to take that equation, you're going to graph it. We're going to go to y equals, and we're going to type in our equation. X to the third plus 2x squared minus 5x minus 6. And we're going to graph it. And we're going to look at that graph. And we're going to make estimates on what we think the zeros are, what we think the roots are by looking at the graph. So we're going to estimate, all right? It looks like we have an intercept at around 2, maybe negative 1, and negative 3. Okay? So our guesses are 2, negative 1, and negative 3. Those are our guesses. That's where we start. We are not done there. And if that's all you give me, no credit. Okay? Pick one, and we're going to prove that it is a solution. So let's look. What did we do to prove whether or not something was a solution? We did the synthetic division, right? And what happened to show that it was a solution? Not the constant was 0. The remainder was 0. So we take one of those numbers and we do synthetic division, doesn't matter which one, and as long as we get a remainder of 0, we know that that's a solution. Sit down on that. Once we get a remainder of 0, what we have left is a quadratic. Then you can factor that quadratic, and then you can solve that quadratic and make sure that those are your other solutions. Or maybe they're not. Okay? They may be something really, really close. Sit down. They may be really, really close, but you need to make sure you're doing synthetic division to get a remainder of 0, and then factoring what you have left to make sure you get exactly what the values are. Okay? All right. Now you make that. All right, so we got cut off, so let's go ahead and finish this up.
So I was saying we're guessing that we have our possible solutions as 2, -1, and -3. So what we're going to do is we're going to choose one of those to be our possible solution and use synthetic division. I chose 2 just because it's positive, a little bit easier. You can choose any one of those 3 numbers. And again, remember, if we are proving that 2 is a solution, we need a remainder of 0. So let's see if that's what we get. Bring it down, multiply, add, multiply, add, multiply, and we do get a remainder of 0. That means that 2 is a solution. So 2 is one of our solutions, and then we look at our resulting quotient. This is x squared plus 4x plus 3. We're going to set it equal to 0, and we're going to factor and solve. So a product of 3 and 1 give us a sum of 4. So we can factor it. We set both factors actually equal to 0. And then we go ahead and solve both of those. And we get x equals -3 and x equals -1. So therefore, all of our solutions are x equals 2, -3, and -1. So we were able to solve that polynomial and factor it completely as well. If we look and see, okay, side note, if we want it factored, we have 2 factors of the polynomial here, and then all we have to do is kind of look at our 2 as a solution and say, okay, well, if x equals 2, the factor is going to be, well, what if I set it equal to 0? X minus 2 equals 0 is my third factor, so we get x minus 2 as the last factor. So we have a complete factorization with x minus 2, x plus 3, x plus 1, and then our solutions are 2, -3, and -1.